So, hello everybody. As Ben said, I'm Alex. I'm a postdoc here at Caltech. My main research is in calibration, so I was asked to kind of go through an overview of how we actually calibrate the advanced LIGO detectors. I think that about the first quarter of this talk is largely going to be review, which I hope you don't mind, but I think that it's nice to kind of let these concepts settle in, and it's also nice for context. Just kind of as a brief outline of what I'm about to tell you, so I'm gonna start with like a very broad strokes, just sort of cartoony picture of how we do calibration. And so this will include lots of diagrams, and there's going to be a control loop that we're going to step through, and everything's going to be great. Then I'm going to give you an overview of how we actually do this process, which is kind of long and involved and convoluted, and we'll get through it. We're going to talk about how we actually track and compensate for these very, very slow changes in the actual state of the interferometer. Things like, changes from lock to lock, like the fact that we don't actually lock on the same point on the mirrors at every single lock. Things like that can lead to changes in the interferometer that we can actually know about. And then I'm going to summarize by kind of, going through how this actually affects the astronomy that we do, and how we can be careful about those kinds of issues. There are a couple of caveats that I want to start with. One is that, like I said, the advanced LIGO instruments are extremely complicated. And the scheme that we use to do calibration can sort of seem like a Rube Goldberg scheme sometimes. And this is really just a flavor. There's like any number of measurements that have to be done, and things break and things change, and we have this SVN repo that's impossible to deal with. So we get there. The next thing is that I am a data analyst, not an engineer, or at least not a mechanical engineer. And so that is the context that I'm going to be providing, is coming at this from a data science aspect. If there are questions that you have about hardware, I will do my best to answer them, but I am hoping that we can also rely on other experts that are in the audience, and we can cover all of our bases. Okay. So because the advanced LIGO instruments are so complicated, I thought that we could start with just something that I think everybody is more or less familiar with from undergrad astronomy, something like that, which is optical telescopes. So the idea that we have in LIGO is really very analogous to what we do with telescopes, which is you want to, with a telescope, you're taking an image of something, and then you want to calibrate how bright that thing appears. And then you're watching for the change in brightness over time. So in that way, I guess, telescopes are sort of power detectors. What you're watching for is the incident intensity from light from a distant source, and then you're watching how that power can change over time. And oftentimes, we have this centuries-old way of doing calibration with optical telescopes, which is to use some kind of catalog of astrophysical sources. Things like stars that are known and well-studied and things like that, and we know exactly how bright they are, and so we know how bright they should appear in an image. And you can use that to calibrate the image of the telescope. More modern telescopes, like this one in Chile, can use more advanced techniques, more refined techniques like adaptive optics, to clear up some of the gunk and kind of compensate for things that happen in the sky, but the basic idea is the same. You're still calibrating how bright something is. And so we don't really take images, right? We're much more analogous to sort of listening to sounds. And so I just, we're gonna step through the instrumentation aspect really fast, and then we're gonna get to how we actually do what we do. So this is just a couple of aerial shots of the actual interferometers that we have, and I think the big difference between, say this and like an optical telescope is the sense of scale, the distance scale involved. So we're trying to calibrate instruments that are massive. They're like 2.5 miles long on a side. This is another aerial shot of LIGO Hanford, which is up in Washington State. And there's one thing that I forgot to mention, which is that this talk is going to focus on the LIGO detectors, and I won't really say much about Virgo or about Cogro or anything like that, but really their calibration is done in a very similar way. This is an aerial shot of LIGO Hanford, and I'm told that there was a mouse cursor, but I don't actually see one. So what we're actually looking for are changes in very, very tiny fluctuations in the length of these arms as gravitational waves pass by. And so right down there in the bottom right-hand side of this image is the corner station that my colleague Jess was talking about in her last talk. That's where we actually have the input laser power, and that's where kind of the control room is and stuff like that. And then 2.5 miles away is where the end station is, and then there is a corresponding thing off to the side of this image Yes, that sounds great. Thank you very much. So off to the left-hand side, out of frame of the image, is the same thing for the Y-arm. And then, these things will bounce off of a mirror, and then they'll come back and recombine. And this is also where we have our main photodiode that we read out the data. But again, we're looking for very, very tiny fluctuations, things that are on the order of 10 to the minus 18 meters or smaller, relative to arms that are 2.5 miles or 4 kilometers long. And I think, as Dave Wrightsey pointed out in his talk, this is like trying to measure the width of a human hair compared to the distance to Alpha Centauri or something like that. So it really is a very, very precise length measurement that we're trying to take. And just kind of to review, this is what it looks like when we're all done. So when everything is stitched together and all the pieces are in place, this is the main data output, which is the strain. And so on the top left-hand, I guess, slow down for a second. Mouth is moving too fast. On the top row here, what we have are time series. These have been bandpassed and notched to show data, I think, between 30 hertz and 500 hertz. And then on the bottom row, you have Q-scans, as Jess was talking about in her last slide. On the left-hand column, you have LIGO Hanford, and then on the right-hand column, you have LIGO Livingston. And I actually made these plots using GWPI, as Duncan is going to point out later today, using open data. So these plots are very easy to reproduce. I actually reproduced them directly from Duncan, so that's all well and good. But this is just showing our first gravitational wave event that we observed, which was the merger of two black holes. So this was GW 150914. And I put this up here just to show how important it is to get this calibration right. So the scheme that we're using is an absolute calibration scheme. And what we're looking for are things like the amplitude of the signal and its phase evolution over time. And it's very important to get both of those things right, because that's how if you're going to fit like a model to it or something, that's how we measure masses and spins and distances and inclination angles and all kinds of other great parameters. And the systematics and like the uncertainty that we have in calibration is going to contribute to all of that, right? Right. The other thing that I want to show is just what the strain looks like, when there is no signal present and when everything is just kind of running in the background. So this I think is taken from the LOSC event page also for 150914. And then in the red you have the shape corresponding to Hanford. In blue you have the shape corresponding to Livingston at the time. And on that day, I guess they were pretty comparable in sensitivity, which you can see by the fact that they kind of line up kind of over here. But down here at low frequencies, there's kind of a mismatch, where Hanford is more sensitive than Livingston, right? But what you can definitely see, I guess, if you kind of squint, I apologize, it's kind of hard to see, but there are these kind of light traces, which is just showing that there's statistical fluctuations in the level of the noise that's in the detectors at a given time. But that is different from systematics that might be there because we might be introducing systematics in the calibration or something like that, which is all things that I'm going to be talking about. The other thing that I want to hit on, that I think somebody asked during Dave's talk, but I can't remember who it was, I apologize for that, is that we have to calibrate this data and get it out very quickly. So we calibrate it within about 5 seconds. And the idea in doing so is that we're looking for things like merging neutron stars that can have optical or EM counterparts. Electromagnetic counterparts. And so in order to search for those kinds of things, we need to package this data and get it out the door very quickly, and then to search for actual signals, within like a minute or so. So the calibration is the first step in that process, and it needs to be handled, in real time. And that's actually done at the sites, so it's done at LIGO Livingston and LIGO Hanford, but there's also a process in place to kind of stream that data also in real time to other supercomputer clusters kind of around the world. There are several in the US, but there's also one in Germany, and I think there's one maybe in India or somewhere. But the idea is that at that point, those computer clusters can have data analysis pipelines that are just kind of running all the time. They receive the data, they search for these signals, and then they put out alerts to astronomers if they find something. And I believe that this is something Alex Nitz is going to talk about maybe tomorrow. Okay, so why don't we just dig into it? So this is really the only diagram of instrumentation that I'm going to be showing, again, because I'm a data analyst, and that's just kind of how things work. So what I want to do is to just sort of step through the process of how a passing gravitational wave would actually impact the detector, and then how we would record that, because I think that that will inform how we actually then calibrate it. So the idea is that we're trying to sense these changes in length, and when these changes in length will happen, it'll cause the mirrors to sway relative to one another in some kind of sinusoidal fashion. And when that happens, this photodiode that we use to read the data out will see a change in the laser light. And that is the direct thing that we measure. That is the thing that we measure out, and then we reconstruct the strain from that. Right? So what we don't do is measure the change in length directly. Instead, we're reconstructing it from this change in the laser light on that photodiode. And because there is an extra step here, which is that we have to hold the arm cavities in resonance. They have to be in resonance in order for us to be observing. So there has to be some control in this situation. And the way that we do that is by using these actuators. So this inset, I guess on the top right-hand side of the figure, is just showing you the actual test masses. There are 4 of them that are suspended, in chain. In series. But each of them has, some electromagnetic actuators, and we use this to control the actual stability of the mirrors, and to hold the arm cavities in resonance so that we can continue observing. So I think a much more intuitive way to visualize this process is with this control loop. So I don't know how many of you are used to looking at control loops, so I'm just going to step through it, and we're going to see what happens. Right? I apologize if I'm belaboring the point a little bit, but I promise that this is really important for what comes next. So what we're trying to reconstruct here, what we derive the strain from, is this object delta L free. So strain is just delta L free divided by the length of the arms. It's delta L free divided by 4 kilometers. So it really is, that's the change in length that we're trying to measure. And so this delta L free is going to contain things like gravitational wave signals, but it's also going to contain noise, right? It's going to pass through, and then at this plus sign, what we're doing is we're subtracting a controlled length change, which I'll talk about later. It'll be the end result of stepping through this full loop. But so there's a length change that we're controlling for, and then as a result of that process, there's going to be some residual, right? And then the residual is going to affect the shape of the mirrors, or sorry, the stability of the mirrors and everything. There will be some laser readout, and then we use the laser power that we read out to feed it back in, and that's what you see here. We use the signal that we get out to kind of actuate back against the mirrors to hold them in resonance. That's delta L control. We subtract that off, and then the whole process begins again. Right? So I don't know if that hangs together as something that's clear. But so just to make this a little bit less abstract, delta L free is the gravitational wave that's sort of passing by and everything. The sensing process, so this process right here, just refers to the actual motion of the mirrors. And then we read out the laser power on the photodiode. We pass that signal back to these actuators to hold the arm cavities in resonance, and then that's the whole cycle. So that's what happens when the interferometers are locked and observing. Okay. So I'm going to kind of like step through and talk about what happens in each of these little boxes. So the first one that we have is what we call the sensing function. And so the sensing function just sort of, it refers to the act of sensing a change in length. And so this is how we go from the signal that we're trying to reconstruct, the change in length, to the signal that we see at the photodiode. Right? So we're going to think of this as a digital filter. It's a linear process. So what happens is a signal comes in, it's affected by the sensing function, and then a different signal is what comes out. And that's the signal that we actually see. Right? The filter that does that is what's plotted right here. So this is a Bode plot. I don't know if there's any engineers in the room, but the top just shows the magnitude, and the bottom shows the phase in the frequency domain. So this is a function of frequency. And if you're trying to build a physical intuition for this plot, what it's really telling you is the bandwidth of sensitivity that our detector has. So the shape of this plot is kind of, in a way, it's what shapes the actual sensitivity curve that we have that I was showing you before. It's what shapes this plot. What I've plotted is actually slightly different from this. It's actually 1 over this. And that's because we're trying to go to the left. So we're going from this signal, the error signal, back to reconstruct the residual length change. And since we're doing that, we actually have to take the inverse. So what we see, there's a couple of features that are worth pointing out. One is these kinds of upticks at low frequency and very high frequency. This low frequency uptick is actually below 10 hertz, so it's below where we would ever look for signals. And it's caused by some detuning that happens at Hanford. I actually don't know much about this process, but I can point you to people who do if you're interested in that sort of thing. But then at high frequencies, what we have is actually related to like the average light storage time in the arm cavities. So if you have a gravitational wave passing by that's higher in frequency than 1 over that time, the interferometer is not very sensitive to a gravitational wave at that frequency. And so what happens is it doesn't affect very much of a change in length. So we have less and less sensitivity at those frequencies, right? And because we're plotting the inverse, we see an uptick. The next piece that I think is pretty important is what we call the actuation chain. And these are the filters that actually go from the control signal and then feed out into the mirrors. So this is how you actually go from the signal to control the mirrors, and then you pass it to them, and that's how they know what to do with it. And in this case, it's also very similar. So this is, I guess, if you like, this dotted line in kind of bright violet is the total of the entire chain. So this takes all 4 of the test masses. Sorry, I'm going to go back to this plot right here. It takes all 4 of these test masses, and kind of totals up the response of them, and that's the sum total for each of the test masses. The other pieces are kind of shown individually, and what you can see is that different pieces of the actuation chain dominate in different frequency regimes, right? So at very low frequencies, the dominant contribution is kind of from, I guess it's from the penultimate upper mass, and it's from the upper intermediate mass. So these are, this is complete jargon, I totally apologize. But I believe, so this is referring to things like these two chains right here. Okay. But the main point of this is that what you see down here, so we're going to focus on this dashed line. And in this phase diagram, you have no turnovers between about 10 hertz and 2,000 hertz. So this region right here is where we're detecting most of our signals. And we're preserving the phase, and everything is stable and golden. So the next thing that I actually want to point out is the calibration lines. I know that there have been a couple of questions about this in the morning talks. And so just to kind of give like an overview of why we do calibration lines and what the actual point is and how we actually get them into the detector, I think is worth spending a couple of minutes talking about. So what I've shown on the top row is just an amplitude spectral density. So this is the same thing that Jess was talking about, where we're just visualizing the strain signal in the frequency domain. And what I've done is I've taken I think something like 100-second FFTs so that the frequency resolution is very, very fine. And then so what I've done is I've plotted at 3 different kind of frequency ranges. This is at very low frequency, around 20 hertz. This is mid-frequency, that's right in the middle of what we call the bucket. This is the middle of where we're most sensitive. This is around 300 hertz. And then there's an extra line that's right above a kilohertz. And so we put these lines in for several reasons. One is just to check how well we're doing. Right? So the idea is that you have some kind of change in length that you introduce on purpose, some kind of signal that you put there so that you know what it should be, and so you can see how well you do in reconstructing it. Right? And this actually turns out to be a pretty good idea because this gives us an idea of like systematics and stuff like that, which I'll show you in a second. But so I think the line that's most important is this one around 300 hertz because, like I said, it's right in the middle of where we're most sensitive. And as for the way that we actually put these lines in, so we actually use like a small little side laser that we call a photon calibrator, or PCAL. And so what we're doing is we're actually using the fact that photons carry momentum, and so when they strike the mirror, they impart some of that momentum. It's not very much, but we're also measuring very small changes in length, right? So they impart some momentum onto the mirror, and that causes the mirror to move, right? And then by controlling the input of the signal, what you get back is just motion of the mirror that you intend to put there in a controlled way. And so we have these three calibration lines that are running continuously all the time, but we can also use the same system to do things like hardware injections, which I don't think there are any talks on in this session, but you've probably heard about them before. So hardware injections are just a way of simulating our response to actual signals, you know, in the course of doing an observing run or something like that. But this is kind of the system that we use to do that. And so I think a good question to ask at this stage is, like, you know, you've just passed the baton. You've just moved the goalpost. So now you're going from calibrating strain to calibrating this new laser system. And I actually didn't fully appreciate until very recently that we actually calibrate this laser beam from NIST, the National Institute for Standards and Technology. You know, this is where we get information about timing and sort of the laser power and stuff like that. And this laser system is calibrated to, I think, better than 0.5% in magnitude, which is much, much better than we actually do with LIGO. So it's a very minuscule impact on our calibration scheme. The other thing that I want to point out about the calibration lines is that in O2, data cleaning can actually remove these lines so that they don't become a nuisance for searches for signals or things like that. Because that's another thing that we have to worry about is, like, you know, any potential pulsar signal that we see from like a galactic Milky Way pulsar might happen to live near one of these lines. And so you want to make sure that you're not polluting your signal space, things like that. Is there a question right there? We could have. We just didn't. I think it was really a person power issue. Yeah. I think in 01 we were just kind of strained, pardon the pun. Yeah, sorry. Anyway. The other thing that the calibration lines are useful for is to track these very slow changes in the state of the interferometer. So we have calibration lines that are injected at 3 different frequencies. And it's actually a different set of frequencies at Hanford and Livingston, and the set of frequencies at Livingston actually changed during O2. So where the lines are actually placed is time dependent and instrument dependent, but the idea that there are 3 lines there, you know, is stable. And so what we want to do is we want to get rid of systematics in the final data product that we release, which is the calibrated strain. And one way that we work on doing that is to kind of treat these very small scale oscillations or small scale variations in the scale of sort of the sensing and actuation functions, right? And so we treat these as sort of like an optical gain or a scale factor, right? And they're all at the level of, say, 10% or less, right? And so what we're doing is we're kind of visualizing how these things change over the course of, I believe this was from 01. And I pulled this from this paper, which you can go and read if you want to learn more about it. But the idea here is that, you know, these fluctuations are all at the level of like a few percent. They're not very big, but they do cause systematics that are, you know, kind of problematic for data analysis. There is one other thing, which is this last parameter down here, which we call the coupled cavity pole frequency. This is the thing that's related to the average light storage time that I was talking about earlier. And this is the thing that actually sets the bandwidth of sensitivity for the LIGO detectors. And this is a parameter that can also change from lock to lock or from day to day or month to month. And so this is also something that we want to track and in principle compensate for, but it's been difficult to do that in the past. Because this is actually like I'm going to go back to this plot. And this would so changes in this frequency cutoff would actually change it would change the shape of this curve. So it's both time and frequency dependent, which makes it very difficult to compensate for. But there's a scheme in place to do this, and this is one of the things that we want to do for O2. I think the plan is that we're going to release it at some point, but I don't want to make any specific promises. Okay. And then I just kind of, to sort of close out, I just want to talk about the systematics that we actually see and how we deal with them in the data. So what I've done here is I've taken, sorry, I'm going to go back here. I've taken this red curve, which is, how do I want to say this? This is the strain out of Livingston that's been corrected for the scalar fluctuations, but not for the cavity pole frequency. So in principle, there should still be some systematics left in, but it's better than nothing, is the idea. And I'm reading off at this one particular frequency and comparing that to this sort of teal shape, which is the photon calibration laser. And so the idea is that I'm trying to compare the final data product that we see to my input and see how well I'm doing in reconstructing the data, see how well I'm doing in reconstructing what I think should be there. And what you can see is that we're not doing bad. So all of the systematics that you see are well within the range that we have set for ourselves, prior to the start of O2. And I think that this data was taken around January of 2017. So this is data that's around the binary black hole candidate from last January, 170104. And so what you can see is that this column right here is the line at 23.3 hertz. This column right here is at the line at like 300 hertz, and then this line right here is the line, sorry, this column right here is the line above a kilohertz. The top row is magnitude, and the bottom row is phase. And what you can see is that differences in the magnitude between what we get out and what we expected to put in are something like at the level of less than 2% at this low frequency line. They are a little bit better at the mid frequency line, and they're pretty good at the high frequency line too, although that has more statistical fluctuations. And the story in phase is also pretty similar. So the story in phase is really, really good right at the mid-range frequency, which is awesome for our searches. Because again, that's where we have the most sensitivity, and measuring the phase is where you're going to get things like, or it's where you're going to get information about things like mass and spin and stuff like that. If you want a full picture, there was also another paper that we put out recently that was kind of spearheaded by a grad student in our group, Craig Cahalan, who I don't think is here. But so this is just sort of showing the full frequency dependence of those systematics. And so what you would want to see ideally is that this top plot in magnitude should just be 0 all the way throughout, and then this bottom plot should also be 0. But of course, we don't work with ideal detectors, and so there's always going to be some level of systematics. But what you can see is that they're always, at the level of like a few %, which is very manageable. And then in phase, it's even a little bit better than that. Maybe you have, things like at the level of 2.5 degrees or less, which is good. This is the uncertainty at Hanford, and this is the uncertainty budget at Livingston. I guess I messed that up. This is for Livingston. But the story is qualitatively very similar, even if the details are different. Right? So in conclusion, the advanced LIGO calibration is good, and it's getting better. Strain is calibrated with more precision and less systematics in O2 compared to O1, and that's just because we had improvements in the software and stuff that we actually used to do these things. We can now track and compensate for these slow variations in the interferometer, and we can reduce systematic biases. And then in the future, we plan to kind of do this process much better. I also want to point out that there's actually some functionality in GWPI that you can use now to do many of these tests on the calibration lines. And I've just included an example right here. But I think that Duncan MacLeod is not going to talk about this specifically probably, but we will talk about GWPI and how to use it. But that's the spiel I had prepared. People can feel free to ask questions.